One of the advantages of Symbulator being a symbolic simulator is that dependent sources can be described with no special nomenclature. Dependent sources are, for description purposes, regular elements in Symbulator. They are simulated just as independent sources, with the only difference that its values are given in terms of the variables upon which they depend. Let me provide you with some examples of dependent values of sources. For example, let's see if the value is dependent on current. As you know, for every resistor we have in Symbulator, there will be a variable created called I and the name of the resistor that is going to have the current of that resistor flowing from the first node to the second. So let's say that there is a source whose value is twice the current through a resistor called R1. In that case, the value for that source would be described as 2IR1. What if we have that the value for the source is half the current through a resistor RA? Well, we would say the value is IRA divided by 2. Pretty straightforward. If the value was dependent on voltage, let's say twice the voltage drop in a resistor R1. As you know, for every resistor, a variable will be created called V and the name of the resistor, including the voltage drop in that resistor, meaning the difference in voltage between node 1 and node 2 in that resistor's description. So we can say 2 VR1, and Symbulator will understand that this means twice the voltage drop in that resistor. For example, half the voltage in resistor RA is VRA divided over 2. And if you have, this happens sometimes, it could be like a constant times the voltage drop, or a constant times the current. So let's say that we have X times the difference in voltage between node A and node B. Well, then you would say X, if X is a constant, or mu, or whatever it is, times, and then you, between parentheses, you put voltage A minus voltage B. These are just examples. Now let's see one example, and in the next lesson we will see a much more comprehensive example. Okay, so this is the circuit. You can see that I have labeled the nodes. The bottom node that is not labeled is the ground, so it's 0. And we have here some elements. This is how I describe them. The independent source between A and 0, I'm calling E, the value of V1, resistor 1 between A and 3, value of R1. And here we have the resistor whose voltage drop is going to control the dependent source. So we have to make sure that we define as the first node the one where the voltage drop is defined as positive. So we say RG between 3 and 0 with the value of RG. You don't want to say between 0 and 3 because you will be reversing the polarity. Now to describe the dependent source, you would say J, because the current source, from 2 to 0, and the value is a constant Gm times the voltage drop in resistor G. So you say VRG. That's the voltage drop in resistor G. And then you have your resistor RD, nothing there, and resistor RL. And here the question is to find V2. Now this is how we would find V2. We would describe the circuit just as I mentioned before. Source, voltage source E between A and 0, value of V1, resistor 1 between A and 3, value of R1. This is the resistor now that is controlling the dependent source, RG between 3 and 0. We use the right polarity, value of RG. Current source of J between 2 and 0, the right direction for the current, with the value of Gm, which is a constant, times the voltage drop in resistor RG. We have the resistor RD between 2 and 0, and resistor R1, I'm sorry, RL between 2 and 0, with the value of RL. You have to be careful because the L and the 1 are very similar in the calculator. So we paste that description. We're going to pass it as a string right inside the DC program, and we're going to say, you know what, give me the value of V2. We overclock the emulator so that it runs faster, and we get the expression for V2. You can compare it with the expression given by the textbook, and you can see that it's exactly the same thing.